So in exercise number 7, we are revisiting an exercise which I have showed you before. So this will be the only real calculation exercise of this recap session because I wanted to make sure that this recap session is a recap session where we talk more about verbal exercises and intuition, and the previous recap session from last week was more about calculation. But since this exercise here, I've shown you this exercise, I think in problem set number 5. And I did some slight mistakes there, which maybe created some confusion, and therefore I wanted to make sure that I do one more type, like exercise of this type, just to show you that, yeah, it's basically not very difficult because the steps are actually quite simple to follow, and I wanted to reduce the confusion, which was basically caused by me the last time that I dealt with this exercise. Yeah, so that's why we will consider this exercise here again. So this will be the last exercise for this week. The demand for apples is given by QA equal to 100 times 100 minus 5 times PA, and the supply of apples in Brahma is given by 30 plus 10 times PA. The demand for bananas is given by 300 minus 40 times PB, and the supply of bananas is given by 120 plus 3 times PB. Both goods are currently untaxed, but the government needs to raise 1,000 euros by taxing apples and bananas. What tax should it levy on each of the two goods if it wants to tax the consumption of apples and the production of bananas? So I also introduced some kind of variation here in what side of the market is taxed for which type of good. So, okay, let's go and solve this last exercise. Good. So let us first start with apples. So what we need to derive first is the marginal tax revenue of a tax increase for apple and the marginal deadweight loss of a tax increase for apples with respect to apples. And then we need to do the same thing for bananas. So without tax, the demand is given by the following. The demand for apples is given by 100 minus 5 times PA, and the supply is given by 30 plus 10 times PA. With taxes, oh, sorry, with taxes, what we have is that the demand is equal to 100, so there will be a change in the demand function. It's 100 minus 5 times PA plus TA, which is the tax on apples, and the supply side will remain unchanged. So the equilibrium price is the first thing that we need to find out. For this, what we do is we set equal the demand and the supply function. So 100 minus 5 times PA plus TA. This is supposed to be equal to 30 plus 10 times PA. And if you solve this, you get an equilibrium price of 14 divided by 3 minus TA divided by 3. And if you plug this in to either the demand function or the supply function, you get the equilibrium quantity. Let's plug it simply into the supply side, which is then 30 plus 10 times PA star, and this is equal to 230 divided by 3 minus 10 divided by 3 times TA. Now we first calculate the deadweight loss for tax on apples. The formula for this is given by 1/2 times the tax on apples times the change of the quantity demand, like traded, the change in quantity demand, or the change in the quantity which is traded on the market when we consider taxes. And this is simply 10 divided by 3 times TA. So if we plug it in, we have 1/2 times TA times 10 divided by 3 times TA. And the reason why this is the change is basically that if we set TA equal to 0, we end up with the quantity which is traded without the tax. And due to the tax, we have a reduction in 10 divided by 3 times the tax itself. Yeah, so this is how you know what the change in quantity due to the tax is. And yeah, if we calculate this, we have a deadweight loss of 5 divided by 3 times TA by the power of 2, and the marginal deadweight loss, therefore, so the marginal deadweight loss for apples is then simply the derivative of this expression of the deadweight loss, and this is then 10 divided by 3 times TA. So next, what we need is the total revenue, the tax revenue due to a tax on apples. This is simply the demand of apples traded times the tax which is imposed on apples. And then this is simply 230 divided by 3 times TA minus 10 divided by 3 times TA by the power of 2. And yeah, the marginal tax revenue then for apples is then simply the derivative. So it's 230 divided by 3 minus 20 divided by 3 times TA. Yeah, so those are the two things that we need for apples. So the marginal deadweight loss and the marginal tax revenue. So let's go to bananas. Let me just separate it here. So let's go to bananas now. So the demand is 300 minus 40 times the price of bananas. And the supply is 120 plus 3 times the price of bananas. And now here we do not have a tax on consumption, but a tax on production. So there will be a change in the demand in the supply side. So with taxes, we have a demand which is equal to 300 minus 40 times PB. No changes here. For the supply side, we now subtract the tax on bananas from the price that a supplier is receiving. So then it's 120 plus 3 times PB minus TB. Okay, so this is now the supply and the demand curve for bananas. And the rest of the steps are the same. So the equilibrium price, we can find this out again by setting equal demand and supply. So this is something that you should be able to do even when you're sleeping. So 120 plus 3 times PB minus TB. Yeah, so the taxes on bananas are here denoted by TB. If you solve this, you get an equilibrium price of 180 divided by 43 plus 3 divided by 43 times TB. And plugging this into the demand function, for instance, so QB star is equal to 300 minus 40 times PB star. And if you simplify this, you get 5,700 divided by 43 minus 120 divided by 43 times TB. Now the dead weight loss for bananas is given by 1/2 times the tax on bananas times the change on the quantity, or the quantity traded in the market of bananas due to the tax. This is then 1/2 times TB times, again, this expression here, of course, in the strictly positive term here. So 120 divided by 43 times TB. And this is equal to 60 divided by 43 times TB by the power of 2. And the marginal dead weight loss for bananas will therefore be 120 divided by 43 times TB. Now the tax revenue for bananas is then simply the quantity traded times the tax. And this is equal to 5,700 divided by 43 times the tax on bananas minus 120 divided by 43 times TB by the power of 2. And if you take the derivative, you have the marginal tax rate on bananas, which is then not the marginal tax rate, the marginal tax revenue, 5,700 divided by 43 minus 240 divided by 43 times TB by the power of 2. Not by the power of 2, just TB. So now we have everything that we need. So, oops, wrong one. We have the marginal tax revenue, we have the marginal dead weight loss for bananas, and we have the same thing for apples. And now we can calculate the ratio of the taxes which should be fulfilled to tax in an efficient way to raise $1,000 of taxes, of tax revenue. So what do we need to compare? So we compare the marginal dead weight loss of apples. So 10 divided by 3 times TA. This we divide by the marginal tax revenue due to a tax increase in apples. So 230 divided by 3 minus 20 divided by 3 times TA. This should be equal to 120 divided by 43 times TB, and this is the marginal dead weight loss of bananas, which we calculated before, and from this we divide this by 5,700 divided by 43 minus 240 divided by 43 times the taxes on bananas. And if you solve this, you get the optimal ratio of the taxes on apples and the taxes on bananas, which is then 46 divided by 95 times TB. And this is telling you that if you, for instance, have a production tax of bananas, which is equal to €1, then the taxes on the consumption of apples should be 46 divided by 95. Yeah, so this is the statement that you can make here. So this is only telling you the optimal ratio, but it doesn't tell you exactly how you should tax, so what the exact amount of the taxes should be. So that's what we're doing in the next step. So now we are solving the following problem. So we want to raise €1,000 of tax revenue, and the tax revenue is equal to the amount of apples traded in equilibrium times the tax on apples plus the amount of bananas traded in equilibrium times the tax on bananas. And yeah, if you plug in all the values that we calculated before, so I think I will go on the next page with this because I think I don't have much space here. Let me just copy this. Okay, I don't know why it's not copying it, but okay, I will just continue then. So I will now plug in simply for QA star and QB star. So then what we have is 1000 should be equal to 230 divided by 3 minus 10 divided by 3 times TA times TA. So this is the tax revenue due to a tax on apples. To this we add the tax revenue due to a tax on bananas. So 5,700 divided by 43 minus 120 divided by 43 times TB. And we multiply this with TB. And now we plug in for TA because we know that in optimum, TA is equal to 46 divided by 95 times TB. So if we plug this in, we get the following. So then we have 230 divided by 3 minus 10 divided by 3 times, now in parentheses, 46 divided by 95 times TB times 46 divided by 95 times TB. And to this we add simply 5,700. So there is no change in respect to the revenue of bananas. So 43 minus 120 divided by 43 times TB times TB. And if you solve this equation, so it's a quadratic equation, what you get is the following. So you get TB star is roughly equal to either, now comes the interesting point, which I omitted the last time, but I should have mentioned it actually. So it's either 6.9 or it's 40.6. And as a consequence, TA star is roughly equal to, so here we're simply using the fact that TA star is equal to 46 divided by 95 times TB star. Then TA star is equal to 3.3 if TB star is equal to 6.9 and it's equal to 19.7 if TB star is equal to 40.6. So the reason why we have two different kind of optimal tax rates in order to raise a revenue of 1,000 euros is because there are two ways in which you could kind of get to this revenue. So you could have low taxes on the goods, which imply that the quantity which is traded in equilibrium will be very large. Yep. So you have low taxes, but you will have a very large quantity which is traded. And as a consequence, the tax revenue will be high due to the quantity which is traded. Yeah. So you have low taxes on a lot of traded quantity, and this implies a high tax revenue. But on the other side, what you could have is you could have very high taxes, which imply a low traded volume, like a low equilibrium quantity which is traded in the economy, but you still have a large tax revenue because the taxes are so high. Yeah, so this is the reason why in both ways you generate the same tax revenue, and you do it in an efficient way when you are thinking about the ratio of the two taxes to each other. Yeah, so this is efficient in this way. But there is one other issue which is not kind of modeled here or which is not considered here, and that is the total distortion in this economy. So what you want to make sure is you want to raise the tax revenue that you want to raise, so the 1,000 euros, with the least possible distortion in the economy. So keeping the debt weight loss as low as possible. And now you can think of which of the two pairs is creating the highest distortions, and obviously it's the one, so it's the tax schedule with the higher taxes. So these two things together create high distortions or create high dead weight loss. Okay, so in absolute terms, the dead weight loss in this system, so when you have very high taxes, will create the highest dead weight loss in the economy. So as a consequence, what you should do is you should pick the lowest taxes possible. So TB star is equal to 6.9, so roughly equal to, and TA star is roughly equal to 3.3. And this is the solution to this exercise. And with this, we finish the problem set of this week. And next week, we will simply continue with the topics which are dealt within the lecture. So thanks and see you next week.